Welcome to Unit 1. In this unit, we're going to be doing stuff with similar figures, and in order to execute most of the problems, you're going to have to solve a proportion. So, first of all, a proportion is two equal ratios. And you probably don't need a whole lot of review on solving these because it's an Algebra 1 topic, but just in case, we're going to throw two equal ratios up here with variables. And then we're going to throw two equal ratios up here with numbers. Equals 20 over 30. You'll notice that what happens here when I have two equal fractions, both of those actually equal 2/3, they have the same decimal, 0.6 repeated, is that when I multiply on the diagonals 2 times 30 and 3 times 20, I get the same thing. And that's what always happens when you have proportions, is that the cross products, we call them, A times D will always equal B times C. The minute one of these is off, like if this over here had been a 21, then this would have been a 63, then we say that these are not proportional. So what we're going to do is go solve a couple proportions. The first one's a nice easy one. 4 over k equals 8 over 2. We just say 4 times 2 is equal to 8 times k. We divide both sides by 8, leaving a nice easy k equaling 1. So that one wasn't so bad. On the next one, we're going to do the same thing. We're going to set the cross products equal. We're going to say 2 times, but we need to do the quantity a minus 3. So we need to lock and load it in a set of parentheses, is equal to 10 times 4, which is 40. Then we're going to use our Algebra 1. We're going to distribute the 2 in, multiply it in, 2 times a minus 2 times 3 would be equal to 40. We're going to solve for a by doing the opposite operations to both sides. So we've got 2a is equal to 46. And then we divide both sides by 2 to isolate that a and get the 2's to cancel. And we get a nice a is equal to 23. And we have solved that proportion. On the last one, we're going to do 7 times parentheses x plus 6 is equal to the other cross product, 10 times x. And again, we're going to distribute that 7 in. We're going to multiply it in. 7 times x is 7x. 7 times 6 is 42. That's what will be equal to 10x. Now we're trying to isolate the x, and it's on both sides of the equation, so we need to move it over. This is where we have a choice. We can either move the 10 over to the left-hand side or the 7 over to the right-hand side. And I like to choose the smaller one because I like to avoid negatives. But that's a choice that's 100% up to you. So when I do 7x minus 7x here, they're gone. And that's why I did it, so that I could get all my x terms consolidated over here on the right-hand side. And 10x's minus 7x's is 3x's. Again, we're trying to isolate that x. It's 3 times x, so I divide both sides by 3. And when I do 42 divided by 3, I get a nice 14. So that's how we solve proportions from Algebra 1. And now we're going to apply some of that to some similar polygons. So first of all, we need to put up a symbol for similar. It's a single squiggle. So when you see that squiggle, it means the two things are similar. Well, what does similar mean? Let's define it this way. Two polygons are similar if. Now, before I define that, I want to go off to the right-hand side and talk about some stuff a little bit from first semester. In first semester, you learned this symbol, and this symbol means congruent. And what that means is that your two figures are the exact same size and shape. If you were to overlap them, they would look like one figure. They're exactly the same. All angles, all sides, they all match up perfectly. This symbol is a numeric symbol that means approximately. So when we round, a lot of times we'll change in equals to this if we've rounded. And then this single one I just told you means similar. The difference between this one right here and this one right here is that, like I said, for the congruent figures, they're identical. If you were to overlay them, they would look like one. Similar figures are not exactly the same. They're the same size. I lied. They're the same if they are the same shape. They're exactly the same shape, but it's like one of them's been shrunk down or blown up. But they're all done so in proportion. It's kind of like me, and I go through a shrinking machine and I become mini me. And when that happens and you've got me, aren't I cute? And I got a little mini me, is that every part gets shrunk down the exact same way. So if this arm is 2 feet long and this is 1 feet long, then if this leg is 4, then this has to be 2, because you can see I'm cutting everything in half. Kind of a weird analogy when we're going to be working with polygons, but that's really what it is. You're going to have a polygon and a mini polygon, like in this next example. It says state whether these are similar. If so, what this means is, go back up here in the box. They're the same shape. What that means is all the sides are proportional. All the corresponding sides are proportional. And I really should put the word corresponding in there, so you might want to write that. All pairs of corresponding sides are in the exact same ratio, and those ratios are equal. Let's go take a look. Who corresponds to 24? 20 does. So that pair, if these are similar, has to be in the exact same ratio as this pair, which has to be in the exact same ratio as the bottom pair, but that's the same as the first one, which has to be the exact same ratio as the left ones, but that's the same as the second one. So really I just have to check and see if these two fractions are equal. And there's multiple ways to do it. I can reduce them both and compare the fractions. I can change them both to decimals and compare the decimals, or I can compare the cross products, which I find more interesting. If you multiply along the diagonals, that 960 along that diagonal, and if I multiply on those diagonals and I get the exact same number, which I did, then I say, yes, those are similar. And again, there's other ways I could have done that. I could have changed them to decimals, and I'll tell you what they are as decimals. 24/20ths is 1.2, and 48/40ths is also 1.2. So the decimals match exactly. I could have reduced the fractions, and those would have been identical fractions. So lots of ways to do that. I like in this section to compare the cross products, but whatever floats your boat. All right, up on the top here, we've got two of them, and we're trying to see if they are proportional. So we're going to check those side lengths. Is this pair of corresponding sides, 10 to 15, in the exact same proportion, or proportional to, same ratio, as 14/21? Let's do this one a different way. Let's reduce the fractions. What goes into 10 that also goes into 15? The answer is 5. I'm going to divide it out, and I get 2/3. What goes into 14 that also goes into 21? I'm going to divide out a 7 and divide out a 7 on 21, and you'll notice I have the exact same fraction. Again, I could have compared the cross products as well, whatever you're more comfortable doing. So last up, I've got a couple of trapezoids here, and I'm going to see if 40 over its corresponding side matches up with 17.3 over its corresponding side. And if that matches up with 29, I have a lot of different pairs here, over 18. And then does that match up? And then I've got this same one again. I've got this same one that's in the middle. So I have 3 different pairs that I'm checking out here to see if they're in the same ratio. Well, I'm going to start with the first pair. Is this truly proportional? Let's check cross products. And I can tell right away that it's not. And again, the cross products is pretty slick sometimes, because I know when I multiply along here, it's going to end in a 0 because of that 40. When I multiply along this diagonal, it's going to end in a 2 because of the 4 times 3. You could go check it out, but those will not be equal. So these are not similar. These were, yes, they were similar. Or again, you could change those to decimals, whatever you prefer. So next up, writing a scale factor. A scale factor is just the ratio of one to the other, and they'll tell you because you don't know if you're supposed to go big to small or small to big. If it's not indicated, it doesn't matter. If you're told, it does. This says smaller figure to the larger figure. So we have to go scale factor of small to large. Now I have to make sure I grab a corresponding side here. These are the two that are equal. These are the two that are equal. So this 5 has to go with one of the 25s, not with the 40. The 40 is on that longest length. So my scale factor is usually given as a reduced fraction, small to large, pair of corresponding sides. And it's done. All right, so next one up here. Let's go label these. I've got two that are the same. So those 18s match up with the 30s. And then I've got two that are different. So I can pick any pair of corresponding sides, small to large. I'm going to pick 21 to 35. And I'd say 21 to 35. I'm going to reduce it. 7 goes into 21 3 times. 7 goes into 35 5 times. And this is called my scale factor, small to large. Now, I could have chosen to do 18 to 30, and if you did, you'd get the same answer. Because they're proportional, the scale factor has to be the same. Divide out a 6, divide out a 6, and I get that same scale factor. So that's the end of video 1. Your task is to complete worksheet 1.1 and worksheet 1.2, and then show me the notes, show me the worksheet, and you'll cruise right along. Have a good one. Peace out, Girl Scout.